So this is the chapter on conic sections, and I'm going to do sections 9.1, 2, and 3, which are about parabolas, ellipses, circles, and hyperbolas. And it's just the introductory page. And the very first word, I like that, astronomical, because I love astronomy, I teach it, and it's great. And we can already see that they have radio dishes here. Lots of applications for all of these here that I just mentioned, parabolas, ellipses, circles, and I'm going to cover a few of these as well. All right, let's look at the first section here. So 9.1 is what I'm going to do here in this recording, which is the parabola. And they start out with this figure here. I've seen this many times. You take these cones here, and technically perhaps we only need one, but not quite true. And notice that when you bisect this cone here, you come up with different shapes. So here at this point, you come up with a circle if you cut it perpendicular. If you cut it at an angle over here, the ellipse should be the next one actually here, you come up with an ellipse. And then if you cut it actually parallel to the side of the cone, you come up with a parabola. And then if you cut it, and I don't think this has to be straight down, it could be at an angle, then you come up with a hyperbola, and that's why they actually have two cones, because a hyperbola will show up twice here and here. So that's a pretty cool diagram to show these, and then later on are the applications. Okay, so here is where they say circle, ellipse, parabola, hyperbola. Okay, and then a bunch of the parabola. I'm not going to dwell on the parabola too much. This is section 9.1, so this is relatively short. They have, because we already did parabola several times before in this class and our previous classes. So they do introduce a number of new words because they're looking at the equation of the parabola somewhat differently. So the new words are axis of symmetry, directrix, and focus. Directrix really reminds me of Asterix and Obelix, Belgian comic book. Anyway, on the very next page, they actually show us the directrix. It's a straight line. It can be horizontal if we have a parabola that opens up or down, or it can be vertical if we have, or vertically if you have a parabola opening sideways. And then we can see the directrix here, the straight line. We can see the focus of the parabola, and then notice these equal distances. And that's what they use in order to derive the equation for the parabola. We see the typical x squared right here. We see the y. This one is new, the 4 pi. I'm sorry, not 4 pi, 4p, which then tells us where the focus is in relation to the parabola. All right. This one here is then a summary of the parabolas that open either up or down, and these are the parabolas that open sideways, and here's the equations. However, there's a second diagram for that, and I like that better because this one will be the general case. So let's see, here it is. Because the general case is actually, it includes the vertex as well. So if it's not at the origin, that was the other one, but if the vertex is somewhere else, here instead of here, again, here instead of here, then we have this h and k, which is the vertex. You can read that here. And so we have x minus h squared, and then 4p equals y minus k. By the way, the 4 here that you find, that was actually in the derivation earlier from the directrix. That's how that came in there. And then they list here the vertex, h and k, and I like to write it as a minus h and a minus k everywhere, because that tells me right away what the vertex is. And then there's the focus, which is almost the vertex, but there's the plus p added to it. You see they're above each other, or on the other one, they're next to each other. So there's only a constant distance away from them. And again, there's the directrix here that tells us where this line is, where the distances are equal, the perpendicular to the parabola, and then from the focus to the parabola. And I think it was actually really invented to show how to draw a parabola. And so I actually had to look at what are the applications of the parabola. So I came up with this one here. I think this is math stack exchange. There we go. You can read that address there. So I actually really Googled the question and said, what is the importance of the directrix? So they have a number of things here. So this person actually asked, I know what the focus is for, satellite dish, whispering galaxy, and so on. But what the heck do we do with directrix? So this person here comes up with that, say you're walking along a parabola-shaped path when you see a bear at the focus, and then you're trying to stay safe, and there's another bear, and so on. Interesting way of looking at that. And then he gives another example. Say there's a parabola-shaped lake, and you want to build two perpendicular roads. And then where do you put the crossroads of these two perpendicular roads? Well, anywhere on the far side of the directrix. So there come some interesting ones that are coming up here, why the directrix is important. Let's see, there was another one here, I thought. If you throw a ball, then ignoring air resistance, we have a parabolic trajectory and so on. And then the directrix of this parabola is a horizontal line. The set of all points at certain height in the parallel plane. This height is the energy in the ball. And that one I personally can understand because I teach physics. So the kinetic energy plus the potential energy, which is what it says here, is equal a total. And so looking at the directrix, you can figure out, or I could figure out as a physicist, what is the total energy and then compute either kinetic or potential energy from it. Anyway, I actually had to Google that too. What's the importance of the directrix? The book really doesn't say that. All right, let's go back to the book here. And then there are, so after this general table, I like this better than the other one because the other one was really only on the origin. There is a number of examples. And I'd just like to go directly to the problem section and do a couple of problems. And I think the problem that I chose is number 26. So here it is. X squared equals 8 times y plus 3. So obviously for this one I use Desmos. So here it is. You can see x squared equals 8 times y plus 3, exactly the way it is in the book. And I did write a little bit different. Notice my minus 0 here because again, that 0 right here and that negative 3, actually this I do want to rewrite as minus negative 3. I should have done that earlier, forgot, because that tells me right away where the vertex is. So again, here's my equation for the parabola. There it is. And then here is the 0 and the negative 3. And in fact, there it is. 0, negative 3 is the vertex. So writing it that way tells me right away where the vertex is. The focus here, I had to compute myself, respectively, just plug it in. The focus is the 0 right here, and then it is the other one over here, the negative 3, which is the k, and have to add to that the p right here. That's also why I wrote the 8 as a 4 times 2, because a 4 is a given in the parabola equation, but times the p, so in this case the p is 2. So I add it to it, and I come up with the focus, which is right here. And then yeah, right here. I don't know if I can click on this, maybe not. It's labeled. And then the directrix is that negative 3 from over here. Yeah, it's good that I rewrote that from the y plus 3 to a y minus negative 3 because it's easier to see. So that's the k over here, negative 3, and then there's a minus the p, so 2, minus 2, then gets me down to 5, and the directrix is here. And again, the vertical distance from a point on the directrix up here to this point here on the parabola is the same distance as this. This is what they're trying to tell us in the book. And or a better one to see is actually when we go right here where we are 4 away. So up is 4, and then over here is also 4. That obviously is the same number, so it's easy to see here. Something else to point out, perhaps, they don't have this necessarily in the book, are the x-intercepts. So notice the x-intercept are close to negative 5 and 5. They're not exactly 5. We can actually check that relatively quickly. So minus negative 3 is plus 3, of course. 3 times 2 is 6, times 4 is 24. Take the square root of 24. Well, if you take the square root of 25, you come up with 5. If you take the square root of 24, you come up with something close to 5. 4.9, by the way, and that's kind of what we can see here. There it is, and here it is, negative and positive 4.9. All right, and then I found this one here. So I actually Googled kind of Desmos, parabola, focus directrix, something like that. And I came up with this person here doing it. So we have the equation over here. Here again is the general equation. And the h here in this particular case that I chose was 0, the one from the book. So I'm going to shift that over here, 0. The p is a 2. There we go. Notice all of a sudden that turned the parabola over from upside down to right side up. And then the k here is actually -3. So I'm going to push that down here. And now when you look at that, right there, I had it. There we go. There we go. That's exactly the same as what I did myself. I'm going to zoom a little bit out. And again, we can see the x-intercepts are close to -5 and 5. The focus is at 0 and -1, and then the vertex 0, -3, and the directrix is as -5, just like I did it over here. All right, let's do another problem. I chose 51. So this one here, figure out what the equation is with just given this information, the vertex at -2 and 1, directrix at -2. And I know it doesn't say to graph it, but I will graph it anyway. So my vertex is -2 and 1. And again, I already prepped that one here. So here's -2. And what does it say? Ooh, what did I do? Let me fix it. Oh, I know what I did. I made this too narrow here. Here's my 1. So -2 over here and 1. That's actually the vertex right here. Then it says the directrix is -2. So I just type this one in -2 plus 0 here. That 0 just has a different meaning. All right, we just had some internet problems here, so I hope this is going to work. So here's my focus. This one looks a little strange here, the p here, 1 minus -2. But when I look at the equation for the directrix, I notice that hey, I'm going to take the k, which is the 1 over here, and I subtract from it the directrix, which is this one here, and then I come up with the 3, which I also wrote down for the focus. For the focus, it's 1 plus 3, that 1 plus the 3 right here, and that gets me focus with the original -2 right here. And again, if I go over to the other one, and I have to remember which numbers these are. So I have a -2, and I have a 1, and I have a 3. So -2 is the h, the 1 is the k, and the p was a 3. There we go. Again, when I put that in, that's exactly, the focus is here at -2 and 4, the vertex -2 and 1, and the directrix is -2, and then it opens like this. That's exactly the same thing that I have over here. Here's the -2 and 4, -2 and 1, and then here's the -2. I know it looks a little wider here, but I think one of the scales is a little bit different than the other one. And these are a couple of exercises for the parabola. Then after that, I'm going to go back over here. They do have a number of applications here. So they're talking about satellite technology, satellite receiver, landscaping, design, auto technology, road paving, parabolic mirror. There should be also astronomy somewhere in here. So all kinds of cool applications. And if we were really in the classroom, I could actually expand much more on that. All right, that's it for this section. Actually, it did take me 14 minutes to do that. All right.